Hey, welcome guys. So previously I already talked about the direct product. If you haven't seen my group theory released, I will post the link below. Yeah, so this video I still want to talk about direct product, but using a different approach. And after that, so basically the whole points in the next video is try to prove the following: is that all the finite abelian group is a direct sum of cyclic or a direct product of cyclic. Okay, so B basically means that every, let's say A is abelian, then A can always write as, let's say, N1, N2 up to Nk. And every is every guy which is cyclic. Yeah, you can prove this by using if you know about like find some module define a principal ideal domain can be direct sum as a cyclic module. You can use the more powerful theory like module theory, right? But I try to prove I try to establish some step-by-step approach. I mean, so at least in the group theory combined with the Cito's theorem, we can prove this. Yeah, but I will prove in the next video. So in this video, I want to talk about more on the direct product. Okay, so let me just quickly say that define a so-called external direct product. External direct product. Oh, by the way, hope you guys subscribe to my channel. Okay, so let's say given A, B, both are group, they are both group, and I can define a Cartesian, right? So A times B, which is each element is AB, which A belongs to A and B belongs to B. And obviously that you can define a group operations that's such that the A1, B1, A2, B2 will be A1, A2, B1, B2. Okay, and the identity is basically the identity. So I use E to be the identity of A. I use F to be identity of B. Okay, so your exercise is to check that now this guy is a group. Okay, and what is the inverse? So AB inverse is basically A inverse B inverse, right? So very stupid. This is E and F. Okay, so this is called the external direct product. So if G is A times B, then we say that G is an external direct product from A and B. And then you can prove, you can also generalize this into like there are many people, right? You can many group, then you can define this. But that's working on, let's say, two of them. And I can consider a subset A bar, which is a subgroup defined to be AF, where second component set to be the identity, and the A belongs to A. Okay, so easy to check that A bar is a subgroup. And yeah, okay, so this A bar is a subgroup, and which is normal, and yeah. The moreover what? A bar is isomorphic to A. Okay, so yeah, this is normal, and the reason is that you can let's create a homomorphism, isomorphism from A to A bar, such that I map A into AF. Right, so obviously that this map is injective, right? Because which is put in the first component is also onto, because given any AF, I can just put A. Right, so this is isomorphic, and also you can define a B bar, right? So which tell you that if G is an external product of A times B, then you can guarantee that there is a normal subgroup which is isomorphic to A and a normal subgroup which is isomorphic to B. But so what we just saying is that if G is a direct product of A times B, that means you can find A, which is A bar which is isomorphic to A, and another B bar which is isomorphic to B, and they are all normal. And but moreover, so there are some constraints that there are some moreover, I can write G bar into G equals A bar B bar. Basically, this means that every G belongs to G has the unique decomposition. has a unique decomposition such that G equals to AB, where A belongs to A and B belongs to B. I should say A bar and B bar, where A bar belongs to A bar, B bar belongs to B bar. Right? And the reason is that every G in G can be written as XY. So I can write XY in terms of XF times Y, right? Because this is identity, this is identity. Okay, so what we conclude the property of the external direct product is that there's a two subgroup isomorphic to A and B, and each element G can be uniquely determined. So this is very important. Okay. Okay, so this is exterior. Let's talk about inner direct product. So this is the different approach compared to my previous one. Okay, so this inner product given a definition. So definition says that let's say G is a group, and the N1, N2 up to Nn are normal subgroup of G. So every guy is a normal subgroup of G, such that the first one is that G equals to N1, N2 up to Nn. So this is as a set, right? So given any G, you can find the element in N1, in N2, and Nn such that their products very G. Okay, so now this product defined to be the group operations start from G. So this is why it's called inner, right? Because in the previously we start from 2A and B and I get something new. But in this, we assume that we already have some group G, and that there's N1, N2 up to Nn here. Okay, and the second is that for given any G belongs to G, there exists M1, M2 up to Mn, such that G equals to M1, M2 up to Mn, and uniquely. Okay. Then we say that G is an inner product, is an inner direct product of N1, N2 up to N. Definition. Okay, so let's do something theorem. Okay, so this is a very simple example that we just prove using the Seidel theorem. So let's say G is a finite group and abelian. So G is abelian. And let's say G's order is decomposed by P1 alpha 1 up to Pk alpha k, where these are distinct primes, and alpha 1 up to just some number. And then you can, let's say, P1 larger P1 and P2 up to Pk are Seidel group of G. Okay, remember that we proved the Seidel theorem, a 3 Seidel theorem. Okay, so Seidel group of G, and then G is what? G is the internal direct product. So G is the internal direct product, internal of the direct product of all the Seidel group. Okay, so this is the theorem that I will not prove here, but I will prove in the next video. Okay, okay, so now the rest of video is to show that I want to show this. So I want to show the inner direct product is actually the same as the outer direct product. So what I just described two are actually related and they are isomorphic. Okay, but before to do this, we need the following lemma. So let's say that lemma is that G is a inner direct product of this N1 up to Nn. Then for I a J such that I do not the same as J, and then Ni and J intersection will be identity. And if A belongs to Ni and B belongs to Nj, then they will commute. So I want to say that if G is the inner direct product of this normal subgroup, then it must be their intersection is identity. Okay, this is very weird, right? So this should come from uniquely. Okay, and these are also a little bit weird. If they are different than different sector, then it must commute with each other. Actually, if you prove this, then I guess you are already very, very close to this theorem. Proof. Let's say X belongs to Ni union Nj, right? So I mean, I can write, let's say X, I can write X equal to E1, EI minus 1, which is identity times X, EI plus 1, up to En, right? So this is the decomposition, right? Because stupid, right? Because E1 becomes N1, and then, yeah, X becomes I. But I can also write X in terms of E1, let's say EI, and let's say X, EJ minus 1, EJ, En. Right, by my definition, inner direct product need to be uniquely, right? So this must be the same, right? So it looks very stupid, right? So X must be identity, X must be identity, right? So X must be identity, trivial. So stupid. Okay, so now this part is trivial, right? So let's work on this part. Let's see what the hell is going on. Let's say if A belongs to Ni and B belongs to Nj and the I is not the same as J, then A inverse will be Nj, right? Because this guy is normal. So Nj is normal, right? So A inverse B inverse will be Nj. And also A inverse is in Ni, right? So B inverse will be Ni. Will tell you that the will tell you that now you can times A here, right? So let's say B inverse is Ni. Sorry, B inverse is Ni. So I can times A here. That become Ni, right? So now this guy, this guy and this guy, these two guys are the same, right? The one both belongs to Nj and Ni. So tell you that the B inverse must be identity by the previous argument. So AB must be BA. Who cares? Okay, so notice that uniquely is very important. Uniquely is very important. If you lost the uniquely, then all the theorem will be false. Okay. Okay, so let's go to our final theorem. This final theorem says that if G is a group, and G is an internal direct product, let's say N1 up to Nn, and let's say T is the outer direct product. So I use a different notation, right? So no one can stop me to using these two different notations. So this is inner, so this is outer or exterior direct product. Then they're isomorphic. So this is what we trying to establish in the. I'm trying to establish in this video. Who cares? Okay, so what we do, we just do the definition, right? We just do the, if you try to get the isomorphism. So let's say phi from T map to G and a simple video, right? So T, every element in T become B1, right? So let's say B1, B2, up to Bn. I map to what? Their product, right? So B1, B2, Bn. Okay, so B is on 2. Right, obviously, right, because you take any G which will detect any G, right, will uniquely give you this, and then you can just put this, right? So clearly phi is on 2, and I want to show that so phi is on 2, right? So phi is on 2, and obviously that you can check which is a homomorphism by yourself. Okay, so the only remaining part is to prove this is okay, so let me see. So if you product, let's say okay, so maybe let's do this to check this is homomorphism. Right, so if you product as this, then this guy in terms of the outer product will be A1 B1, right? So A2 B2, A and Bn, right? So in terms of the inner product will be A1 not inner product, inner direct product, right? And these are all commute, right? Because right, sorry, you just put these right into this, and these are all commute, right? Because these element by different normal subgroup will commute commute, right? So you can check as A1, A2, and also B1, B2. So this will be phi A1, A2, AN, phi B1, BN. So these are all these are homomorphisms. Okay, so finally, we just need to prove that this is injective. So phi is injective. I guess, yeah, this is hopefully looks trivial. Okay, so let's do this. So in order to prove it's injective means that I want to prove what? I want to prove that if phi x is identity, let's say it's identity, then x must be identity. Or basically, I want to, or I want to prove that if phi of let's say A1 up to AN is the same as phi of C1, C2 up to Cn, then I want to prove that the A1 the same as C1, A2 the same as C2, AN is the same as Cn. Right. So now by this definition, this is A1, A2 up to AN, which is C1, C2 up to Cn. Right. And then by definition, the inner product is unique. It's stupid. So by definition, of the inner product of the inner direct product. Okay, so yeah, that's it. So now we have this, and then in the next video, we can just start actually trying to prove that every finite abelian group is there some cyclic. That's it. See you guys next videos.